Hey everybody, p-brane here. This video is about the clockwise southern celestial rotation that everybody says they see down from the equator south. And they say that it, rotates opposite of the northern celestial rotation around Polaris. Well, what I want to show in this video is that it's not its own rotation, but is in fact just a perspective illusion. It's an anti-rotation, in the same way that anti-crepuscular rays are anti-crepuscular. Okay, and they converge on the opposite horizon to a point much like when they come from the sun. They come and they diverge out and then they converge on the opposite horizon. While the southern celestial rotation is nothing but an anti-rotation of the northern celestial rotation. In the same way that the anti-crepuscular rays appear as though they're coming from a sun on the other horizon. They look the same way that the crepuscular rays do. The crepuscular rays diverge out from the sun, and when you look to the opposite horizon, the anti-crepuscular rays appear to be diverging out from the sun on the other horizon, but they're not. They're just the convergence of the crepuscular rays due to perspective. So it creates this illusion almost as if it's a mirror reflection of the crepuscular rays, so that's why they're called the anti-crepuscular rays. But they're not the source of the light to begin with. The source of the light is the sun. So that's the same way that the stars, the source of the rotation is the northern rotation, not the southern. The southern is just an anti or a perspective produced counter rotation. Crepuscular and anti-crepuscular rays is some strong evidence that perspective will in fact explain that phenomenon. So that's why in fact I'm using the crepuscular and anti-crepuscular rays to show a correlation between Polaris and its counterclockwise rotation and the clockwise rotation in the southern hemisphere. Now you might say, well, how's that? Okay, let's say the sun's overhead, right? And let's say you can see all of the rays coming down. Okay, it would look something like this, with the rays all around you. Okay, so let's attach the sun rays to the sun and let's rotate the sun as though it were Polaris and the stars, but we're going to use the sun. Okay, so as we rotate it, it'd be a counterclockwise rotation around you, right? Okay, now let's take a ground view, right? If you're standing on the ground somewhere and you're looking out to the south, you would expect to see those same sun rays going across the horizon, parallel to the ground, just moving from your left to your right. That would be a counterclockwise rotation from your perspective. Okay, so let's now move the sun down to the horizon. So instead of being overhead, let's say it's in your eastern horizon and it's rising, right? Sunrise. And let's say you have crepuscular rays, all right? They will diverge out from the sun, spread out overhead, and then converge on the western horizon. That's if conditions are right and you could see the anti-crepuscular sun rays. All right, so again, let's attach them to the sun and let's rotate the sun counterclockwise. All right, so what you're going to see is if you're in the middle, you're standing essentially at its equator, right in the center between the sunrise and the sunset, and you would look east and you would see the sun rays rotating counterclockwise. If you look to the west, you'll see the rays rotating clockwise. Okay, because a lot of people say, well, how come you see a rotation when you look south, you see a clockwise rotation of the stars? You know, when actually you look north and the stars around Polaris are rotating counterclockwise. Well, it's exactly the same phenomenon. There's one rotation, but when you look on the opposite horizon, the stars are rotating the opposite direction. And there's an anti-convergence, just like the anti-crepuscular rays converge on the opposite horizon. Okay, so here it is. This represents my sun in the east, and it's sitting on the horizon and has crepuscular rays coming out, and they're attached to the sun. We're rotating counterclockwise, and now here we go, continuing to rotate counterclockwise, still rotating. And as you look in the opposite horizon, or in the western horizon, the crepuscular rays are now visually rotating clockwise as the result of perspective. So it was counterclockwise in the east and clockwise in the west. And just like in my example that I've done so far of the rotating crepuscular and anti-crepuscular rays, the stars also have a rotation and a counter-rotation. They rotate counterclockwise in the north and visually clockwise in the south. Okay, let's break down this picture of the crepuscular and the anti-crepuscular rays. Okay, first off, the red dot, that's the observer, right in the middle. The circle around the observer is your field of view for celestial objects. All celestial objects, the sun, moon, and stars, will go below your visual horizon at about a 6,000 mile radius from the observer. Okay, the diameter of this circle is about 12,000, 12,500, give or take. But all the objects will go below your horizon when they're 6,000 miles-ish from you. Okay, so when you're looking back at the sun is about 6,000 miles away. Let's say the sun is rising in the east. Okay, and those crepuscular rays come up, and when they get to you, so they diverge out from the sun, they're spreading out, and when they get to you, your line here, the divider of the hemispheres, right in the center. Okay, so you're essentially at the equator of the start of the crepuscular rays and the end of the crepuscular rays, or your sunrise and sunset. You have your eastern hemisphere, that would be 180-degree view of the crepuscular rays. And then you have on the western hemisphere of your dome of vision or circle of vision, you have 180-degree view of the anti-crepuscular rays. The rays come up, they spread out overhead, and then they converge on the other horizon, on the western horizon, as anti-crepuscular rays. Now, if I told you to look at this ray going out here, and let's say that ray, look at the end of it, that's 12,000 miles from the sun, you might look out here. You might think, well, that's where the ray is. That's not where the ray is. The ray is right here at the point of convergence for the anti-crepuscular rays. Take a look at any one of these rays. They all go to the same place, you know. Any rays in your western hemisphere of celestial vision, this vision circle, they'll all converge at the same place, 6,000 miles away from where you are, the observer. And I'm going to be tying this into the stars and explain why Sigma Octantis can appear to not move in the sky during the night. So all objects on your anti-crepuscular hemisphere, if you will, that's what I'll call this, 180-degree view, at 6,000 miles away from you, will be at that point of convergence. Now, from the observer, let's break this down into the rays that are 1,000 miles away from you, the anti-crepuscular rays, or look at the crepuscular, either or. But the anti-crepuscular would be this line right here. That's 1,000 miles from you. So that's where all those rays would be at 1,000 miles from you. At 2,000 miles, they would be here. At 3,000 miles, here. At 4,000, here. At 5,000, here. And at 6,000, they go to a point. So we'll get into the stars in a second here, but the stars, like the sun rays, will converge 12,000 miles from the source. Okay, with the crepuscular rays and the anti-crepuscular rays, the source is the sun, and if you're in between, if you're at the equator, so to speak, in between the sun and the end of the anti-crepuscular rays, you will be witnessing 12,000 miles of sun rays that will spread out as they go over you and then converge on the other horizon 6,000 miles away from you or 12,000 miles away from the sun. Well, the stars do the same thing. They have a 12,000 mile convergence from the northern celestial rotation, and if you're standing at the actual equator on the Earth, you would see the stars converge in the southern sky. They would create an anti-rotation, not a real rotation, just the anti-rotation of the northern celestial rotation. Okay, you'll notice how the stars are rising due east and setting due west on the equator line. So if you're on the equator, that's what you'll see the stars doing if you look overhead. Well, the sun and the moon are also circling around the northern celestial center, and they will also appear during equinox and solstice. The sun will appear to rise due east and set due west in a straight line, and that seems impossible. How can a circling sun create a straight line, or, make a straight line straight up and straight overhead? It's just a perspective issue, just like I show here with the crepuscular rays. See how that forms a straight line right here? Let me run this line up. Because that forms a straight line because it's perspective. Everything to the east of you converges and everything to the west of you converges from your perspective. That's why the sun can appear to rise due east and set due west. Okay, let me crop these and set them side by side and have them rotating in the same direction, the crepuscular rays and the stars, just to get an idea. You'll see the similarity. Here's a commonly asked question or a point brought up frequently by the flat earth debunkers. If all the stars are rotating counterclockwise around a northern celestial center, wouldn't the stars, viewed from the equator and you're looking out south, shouldn't the stars appear to drift left or right, counterclockwise, parallel to the ground, continuing the rotation that we see around Polaris in the north? Wouldn't we in fact expect to see that, right? And that's what a lot of people ask. Well, the answer is no, because look at the crepuscular rays and the anti-crepuscular rays, right? As I showed, if you connect the sun rays to the sun while it's on the horizon, like Polaris would be if you're at the equator looking north, Polaris would be on the horizon. And what I showed with the crepuscular rays is if you connect the rays and you rotate it counterclockwise, you would see, as you look to the opposite horizon, the anti-crepuscular rays would be rotating clockwise and converging. So that's what we would expect to see. We wouldn't expect to see the crepuscular rays diverging out from the sun, and then as they go over our head and head for the opposite horizon, continue to spread out, because that's not what we see. We don't see that in nature. What we see are crepuscular rays that are diverging out from the sun, and as we look to the other horizon, we see a convergence of sun rays called anti-crepuscular rays. They don't continue to spread out. They converge to a point on the opposite horizon, because the precedent is set with the crepuscular and anti-crepuscular rays. The fact that they reconverge on the opposite horizon shows us that the stars would have a counter-rotation in the south. So if the crepuscular rays spread out from the horizon and then continue to spread out on the other side of us like this, then yes, you would expect to see the stars circling counterclockwise. When you look south from the equator, you would expect to see them moving left to right and just staying parallel to the ground and just as though one big dish with the center connected, being Polaris or the northern celestial pole. You would expect to see that. That's if we saw the sun rays do this. The crepuscular rays just keep spreading out onto the opposite horizon. But we don't see that. The crepuscular rays become anti-crepuscular rays, and they have a convergence, right? So they diverge out from the sun, now they converge. So the precedent, again, is set that the stars would do a similar thing. I just want to remind you about perspective. Perspective causes everything above us to angle downward, right? The floor angles up and the sky, everything above you angles down. Look at these pictures of clouds, right? They all angle down to the horizon. Everything angles down to the horizon. So does the sun, moon, and stars on a flat Earth. So you can estimate that the celestial perspective, or how far can we see visually objects that are high up in the air, is about 6,000 miles, because that's where everything sets, about a 6,000 mile radius, right? A 12,000 mile diameter circle of vision. It's not where the ground horizon forms, but it is where everything in the sky goes down below the horizon. So keep that in mind now as I show you how the stars are. And let's say the stars actually spread out for hundreds, thousands of miles, let's say, and let's say we can't see them all. We can only see the dome of our perspective vision, which is about a 12,000 mile diameter circle or 6,000 mile radius. That's all the stars we can see. And the stars lower to the horizon at the edge of that circle, of a 12,000 diameter circle. So as you move, this dome of stars moves with you, or your dome of vision, I call it. Anyway, let's check it out. Well, just like, let's say you're standing at the North Pole, right? And the stars rotate. You have Polaris overhead, and the stars are rotating around you counterclockwise. As you move south, Polaris starts to lower in the northern sky, and the stars start to tip. It's almost, I like to think of it as like a salad bowl, right? And so the salad bowl has the bottom is up, that's where Polaris is, and the rim of the bowl is on the ground. That's also where the sun would go around, from your perspective at the North Pole. So as you head south, the salad bowl starts to tip onto its side, and so that, let's say you travel 3,000 miles south of the North Pole, everything would be rising in the northeast, sweeping out over the southern sky, and setting in the northwest, like this, right? And if you go all the way to the equator, Polaris would now be sitting on your northern horizon. The solid bowl would be completely tipped on its side, and half of it would be below the horizon. And now all the stars would be coming up east to west. And so the sun would also rise east to west. And now that's a hard one to visualize. Because if the stars are all rotating like a big disk around Polaris in the sky, a big flat disk, or if they're not a disk, they're a big dome, whichever one they are, if that's the case, and if it's a big flat disk and it's just perspective that's bringing the stars down, well then the people in the south say, hey, well the stars should be rotating just above the horizon, right? And stay equidistant to the horizon as they go around counterclockwise. That's what they'd say we should see. But that's not what we should see. We should see a clockwise southern rotation of the stars. See, we already know from crepuscular and anti-crepuscular rays how perspective works on a grand scale. I mean, that's over 12,000 miles. You see the sun rays diverging out from the sun, and then perspective converges them down to the other horizon. That's over a 12,000 mile span. Yeah, and just a little quick side note here. As I was doing the video, I thought of this. It's like, wow, we could see the sun, right? That's 6,000 miles away from us when it's rising. And if it's throwing out crepuscular rays and then anti-crepuscular rays, and the anti-crepuscular rays are going another 6,000 miles to the other side where they're converging, that's a 12,000 mile total. How is it we can see that on a ball? I mean, that seems to work for a flat Earth, but how does it work for a ball? Anyway, just a thought. And another objection or question I've heard is on a flat Earth, how can four people around the Earth, like these guys here, how can they all see the same stars at night? Well, as you'll notice there, the stars are rotating around, right? I'd ask the question also is, well, how do we see the same sun? Well, we all see the same sun because the sun rotates around and gives us our daytime. Well, the stars rotate around at each other's nighttime. Okay, now I'm going to show each guy, starting with the top guy. There's his little dome of perspective, or his field of view, that viewing circle, right? It's 6,000 mile radius. And the second guy has his night, and he sees the same stars. Third guy, the stars rotate around, he sees the same stars. And now the fourth guy, there you go, he sees the same stars. And that's how that works, right? So now the question begs, and I came up with this question working on this video, and so I'm going to beat anybody to it, is how can Sigma Octantis be fixed in the sky? If in fact it is. They say it is. Okay, I'm going with it. Okay, this is so simple, right? Let's take a look at these crepuscular rays, all right? Now, this is a non-convergent crepuscular ray picture. I just want you to see, okay, that's where you would, if I told you to look out at the end of that crepuscular ray, where would you expect it to be? You might point out there, and it'd say, no, it's not there, it's over here, it's converged. 12,000 miles from the sun, the ray has converged to a point. Okay, let's pretend that these are the stars rotating for a second around Polaris, and let's say Sigma Octantis is rotating 12,000 miles from the North Pole, and I want you to see that it's going to sweep across your entire field of view. In reality, but visually, you're not going to see that, because as we converge these lines the way they're supposed to be, they're going to all go to a point. Even though it's circling across your field of view, it's still going to be converged at one point, because it's 12,000 miles from the source, or 6,000 from the observer. Everything converges at that point. And so there you have Sigma Octantis sitting still all night long. I hope you found this useful. Thank you for watching. Bye-bye.